Hello, welcome to this lecture on computer aided power system analysis. In the last lecture, we have been discussing about the linear sensitivity factors, and in that context, we have also discussed in detail about the very basic concept of generation outage sensitivity factor. Today we will be looking into some another sensitivity factor followed by some other detailed discussion about GOSF. So, what we do is today we first look at that line outage. First look at, we said that in the last class that there are two types of sensitivity factor. One is called generation outage sensitivity factor and another is called line outage sensitivity factor. So, today first let us look at line outage sensitivity factor. It is called LOSF. Similar to GOSF, LOSF is defined as del Pij due to del Pmn. So, what does it mean? It basically means it is a ratio of change in power flow through line Ij due to change in power flow through line Mn. So, we call it as beta Ij Mn, right. So, Ij is the change where it is taking place and Mn is the line in which this change has taken place. So, now suppose I have got a line, let us say between M and N, and if that line is going out of order, that is if this line is getting tripped. So, then therefore, what would be delta Pm? So, if line Mn is tripped, say, then delta Pmn would be when it is stripped. So, then basically the power flow through it would be 0 because it is an open circuit, and earlier is initial value was Pmn. So, it is minus Pmn, right. So, this is it. So, then therefore, when I know this, so then therefore, delta Pij would be minus of beta Ij Mn into Pmn, and so then therefore, Pij new would be Pij old plus delta Pij. So, it is be Pij old minus beta Ij Mn into Pmn. So, then from this expression, if this quantity is known, so then therefore, just by utilizing this very simple algebraic expression, we can simply calculate what would be the new power flow over line Ij in case line Mn is stripped. Now, obviously, if there are, let us say 10 lines, so then therefore, we need to know that what would be this sensitivity factor each pair of line. right. So, then therefore, just as an example, if I have got in my system, let us say 4 lines, and these 4 lines are 2 1 2 2 3 3 4 and 4 1, right. So, I will have, let us say, P 1 2 due to 2 3, P 1 2 due to 3 4, P 1 2 due to 4 1. Similarly, I will have P 2 3 due to 1 2, P 2 3 due to 3 4, P 2 3 due to 4 1. Please note that P 1 2 2 3 and P 2 3 1 2, they are not the same. They will not be the same. We will look into this, but they will not be same. They are not equal to each other, right. And similarly, we will have P 3 4 1 2, P 3 4 2 3, P 3 4 4 1, and lastly P 4 1 1 2, P 4 1 2 3, P 4 1 3 4. So, we have all these combinations. So, what would be this number of combinations? So, now this combination, this is 12. So, it is basically 4 into 3. It is obvious that 4 into 4 minus 1. So, for each of these lines, so then therefore, if I have got m, so then therefore, if I have got, let us say, L lines in the system, L lines in the system. So, then therefore, total number of LOSF, I mean this particular sensitivity factors which need to be calculated is L into L minus 1, number of LOSFs need to be calculated, I would say that pre-calculated. So, then therefore, if I have, let us say, 1000 lines, so then I have to calculate 1000 into 999. So, it is quite a large number. We may say yes, this is a quite a large number, but as we will see in future, in this course only, in some lecture in the future, we will see that these beta coefficients, they will basically depend on the line parameters. And so, then therefore, if I know these line parameters and they have got a and essentially each and every of this coefficient has got one expression, very simple expression to calculate. So, then therefore, it is extremely easy to code that particular expression. So, then therefore, calculating these many coefficients will actually take no time by using the today's computational facility. So, although this number is pretty high, but then basically calculating these coefficients take absolutely no time, because these coefficients only depend on the line parameters, and as these line parameters are known, calculation of this parameter, I mean calculation of this LOFSFs are also very easy. Now, today after this brief discussion about LOSF, we will now look into the detail that how to calculate GOSF. So far we have been only calculating, saying that if we know these particular values of GOSF and if we know these values of LOSF, then we can calculate these new values of power and etc etc. But now we have to now really see that how these GOSF are to be calculated and what form they do take, and until unless we do this, we will not be able to appreciate this advantage of this approach. So, let us look into the calculation of is essentially L phi j k. Now, for this we have to take we need to take, now please recollect the assumptions of FDLF. What was the assumptions of FDLF? What was the assumptions of FDLF? One assumptions is that all Vi is almost equal to 1.0 per unit, and another assumptions was essentially that all theta I is 0 degree. So, then therefore, theta I minus theta j is also 0 degree, right. Of course, they are not 0. Now, here we take another assumption. I mean, when we are calculating of GOSF, that all these lines are completely reactive, that is, the resistances are neglected. Resistances are neglected. So, these are the three assumptions. Now, with this assumption, now suppose I do have a line between bus I and bus J. So, this is bus I, this is bus J. This has got an voltage Vi angle theta I, this has got an voltage Vj angle theta j, and this, because these resistance are neglected, this has got an reactance Xij. This is the reactance. This is the reactance of the line. Reactance of the line. So, with this we know that Pij is very well known expression, Vi Vj by Xij sin theta I minus theta j. So, then therefore, I can write down now, if I apply these two assumptions, if I apply these two assumptions, so then therefore, I can write down Pi Pj is equal to Vi and Vj both are 1. So, 1 by Xij, because both are 1, and this is theta I minus theta j. Because sin theta I minus theta j is almost equal to 0. So, then therefore, sin theta I minus theta j is almost equal to theta I minus theta j numerically. So, we have taken this. So, we have taken these two assumptions. So, we get this expression. So, then from here I can write down delta Pij is actually delta theta I minus delta theta j by Xij. So, then therefore, from this expression, if I know the value of delta theta I and delta theta j, I would be able to calculate the value of delta Pij. Now, how to calculate this value of delta Pij? For this, FDLF, if we look at FDLF equations, what is this first FDLF equation? We have got this FDLF equation B dash into delta theta vector is equal to delta P, right. B dash into delta theta vector is equal to delta P. B dash is a matrix, we already know that this is a constant matrix. Now, what is delta theta vector? Delta theta vector, it is a vector, and B dash is a matrix, it is a matrix. So, delta theta vector is delta theta 2, delta theta 3 dot 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 delta theta n transpose, and delta P vector is delta P2, delta P3, delta Pn transpose. So, from here I can write down that delta P vector is nothing but inverse of this B dash matrix into delta theta vector. We do call it capital X matrix, it is a capital X matrix into delta theta vector. So, we call it capital X matrix into delta theta matrix. Now, because B dash is a n cross n, so it will also mean n cross n. So, then therefore, it should be delta theta vector is equal to B dash matrix to delta P matrix, sorry. So, then therefore, if we expand this. So, we can write down that this is x22, x23. Now, here we are abusing our abusing our notations, but we will just this is x32, x33 and xn2, xn3, xn. These x's are element. Now, here when we are talking about x22, x22 is actually occupying the place 1 1, x23 is occupying the place 1 2, x33 is occupying the place 2 2. Similarly, xnn is occupying the place n minus 1 n minus 1. Please note that this is an n minus 1 cross vector, sorry, n minus 1 cross vector. I made a mistake. This is actually this is n minus 1 cross n minus 1. This is also n minus 1 cross n minus 1. So, this is n minus 1 cross 1 vector, this is also n minus 1 cross 1 vector. So, this is n minus 1 cross n minus 1 vector, right. And although it is the position 1 1, but we are writing it x22 just to denote that this element connects the change, I mean connects the angle at bus 2 with the power injected at bus 2. This element connects angle at bus 2 with the power injected at bus 3, and this element connects angle at bus 3 with the power injection bus 2, and so on and so forth. So, then therefore, please note a very important note, it is to avoid any sense of confusion. Note is that xij occupies the position I minus 1 j minus 1 in the matrix X, This is very important. So, then therefore, from this expression delta theta I would be given by summation k is equal to say 2 to n x xi k delta p k, right. It will be xi k delta p k. So, this would be known. Now, suppose let generator, in fact, because we are taking this case, so let us change this, it will be easier to remember. Let us say the index is L, so I L delta P L from this. Now, let the generator at bus k is out of order. Only. So, then therefore, what happens? At all the other buses delta p k is 0 for k is equal to say 2 to n, but not equal to I. So, all the other buses it is 0 again, I should use L, delta P L is equal to 0 for all is equal to 2 to n not equal to I, and delta P k is equal to minus let us say P k, that we know, right. So, then therefore, in this column there would be only one quantity which would be non-zero, other would be 0. So, right now we would be only taking this expression delta pk. So, then therefore, from this, so from this expression and from this, so we can write down that delta theta I would be equal to x I k into delta pk, because from in this expression if I keep on expanding it, right, L is equal to 2 to n, only delta pk would be non-zero, but all the other delta pl would be 0. So, then delta theta I would be x I k into delta pk. Similarly, delta theta j would be equal to x I j into delta pk. So, then therefore, delta Pij is equal to delta theta I minus delta theta j by small xij. So, this is equal to x I k minus x I, it would be xjk delta pk by xij. Hence, alpha I j k. What is alpha I j k? GOSF, that is the change in. So, this is equal to delta Pij by delta Pk would be equal to xik minus xjk by small xij. So, we write again this. So, therefore, we have got GOSF IJK, that is we denote as alpha IJK, that is equal to xik minus xjk by small xij. So, this is the expression. If we look at this expression, now here in this expression is one or two things very important to note, very important to note. We have to note very important, I would say it is important. I would like to mark that this is very important note. Capital X I k and capital J x k, capital, they are the elements of the X matrix where X matrix is nothing but inverse of the B dash matrix. It's very important. And small xij, please note this is capital Xij and this is small xij. This is the reactance, individual reactance of the line I j. This is very important to note. One should not be confused that this is also the reactance. This is the elements of the matrix A. These two are elements of the matrix A. Now, here we need to note something again. B dash matrix is a constant matrix, that we have already seen when we have discussed about FDLF. Now, because B dash matrix is a constant matrix, so then therefore its inverse is also a constant matrix. So, then X matrix is a constant matrix. So, all these elements are known. because all these elements are known, so then therefore xik and xjk are known, and xij, which is nothing but the reactance of the line, this is also known. We further note that this B dash matrix is actually formed by the knowledge of the line parameters. We have already also seen it when we have discussed about FDLF. So then therefore this B dash matrix is also formed by the or rather or basically the from the knowledge of the line parameter. So then therefore this capital X matrix is ultimately formed by the knowledge of the line parameters, and xij is obviously the line parameter. So then therefore this alpha ijk is a constant quantity for every combination of ij and k. It is a constant quantity, and this constant quantity is only dependent on the line parameters. It is not dependent on any operating condition. So therefore for any given system, the moment we know the line parameters, we can simply pre-calculate these values by this simple expression, and because this expression is so simple, even if these values of I, j and k are very large, very large, but then because the expression is very simple, it is very easy to code, and so therefore it will take hardly any time for the modern day computers to pre-calculate this particular sensitivity factors and to store them. So then what we will do, we will simply first pre-calculate the sensitivity factors and store them, and after that whenever there is an outage of any generator, we will simply recalculate the new power flow over all the lines by the expressions what we have already seen in the last lecture. So this is the basic philosophy. Now let us look, now the question comes into mind that what is the effectiveness of this, that is if I do calculate my new power flow over the lines, obviously because these are dependent on some assumptions, especially of the FDLF. For example, we are taking the assumption that my voltages are all 1 per unit, we are taking the assumption that my angles are all almost equal to 0, we are also basically we are also neglecting the line resistances. So then right, so then therefore it involves some approximation. So the question comes that if we calculate our new values of line power flow by accepting this approximations, obviously those approximate values would have some error. How do they compare if I do the same calculation by running a load flow? So let us see that. So what we have here is, we are considering here a IEEE 14 bus system, and so this is the line data, and so basically this is the bus data. So there are 14 buses. There are 3 generators at bus 1, bus 2 and bus 6, and these are the generator patterns, load patterns, if everything etc. is given. And then here there are also 20 lines. So I have got this 1 to 20 lines, and here also some of the lines are also, for example, these lines are nothing but transformers, these are transformers, these also are transformers, because you see it has got only X, there is no resistance, there is no shunt charging capacitance. So these 5 are essentially transformers, others are lines, and these are transformers that also can be seen by this entries, that transformer tap is 111, others are 0 means that there is, these are basically lines. Now if we do this analysis of GOSF, so we get this. So what we have done is, we have considered the case that this generator at bus 2 has got outage. So here what we have is, in this bus, in this system we have got 3 generators, bus 1, 2 and 6. Out of this, as we have seen, bus 1 we have taken as the slack bus, right, and bus 2 and 6 are the PV buses. So we have considered both the cases one by one. So the first case, we have considered that this generator bus 2 has been out. So when this generator bus 2 are out, and by following this calculation, we have calculated these GOSF values, and these are the original power flow over all the lines. Remember, lines means lines plus line plus transformers. Then we have calculated delta P2. Now this bus 2 has got a generation of bus 2 has got a generation of 18.3 megawatts. So if it is out, so then therefore delta P2 would be minus 0.183. So, this is exactly it will be minus 0.183. So, we have got this, we have got this, we have got original value. So, then we calculate this P line by using that expression what we have discussed. Here we have assumed, so here we have assumed that all these generators which have been lost due to the outage of bus 2 have been taken care of by the generator at bus 1, which is nothing but the slack bus. So, this column shows the power flow which is obtained by this approximate method, and this is the power flow which we obtain by full AC load flow. When we do this full AC load flow, what we do from our database, from this data, we simply remove this bus, we simply remove this, we simply make all of them 0, sorry, with this simply remove this, we say that we have got only 2 generators 1 and 6, right. This 6 also remains the same. So, then automatically this entire extra generation will be taken by bus 1. So, we do this complete AC load flow, and if we look at these entries, they are quite close to each other, they are quite close to each other. So, then therefore, although there is approximate method, but this error involved in them is not much. Similarly, if we look at the case at outage of generator at bus 6, again if we look at these two columns, these two are quite close each other. So, then therefore, what we can see here that this approach gives me very quickly the new values of line flows in the event of an outage of any generator without needing the full AC load flow, and these new calculated values are also reasonably close the ideal values. These ideal values are nothing but the values obtained with full AC load flow. So, because these values are reasonably close with those ideal values, so then therefore, this is a quite powerful method where I can analyze the effect of contingency on or rather we can analyze the effect of generator contingency on any system without resorting to AC load flow very quickly. So, today we stop here. From the next class onward, or rather from the next lecture onwards, we will be looking into the other aspects of this contingency analysis. Thank you.